today's lecture, let us discuss another experimental technique that is called as UV visible spectroscopy, and many a times people just call it as UV-Vis. After going today's lecture, you will get an idea about what is UV visible spectroscopy, the importance of preparing the sample carefully before it can undergo characterization using UV visible spectrophotometer. What is UV visible spectrophotometer? What is the principle behind the construction of this spectrophotometer? How do you collect the data and how do you analyze the data? We will also give you a brief idea about the way you calculate the energy band gap using the UV visible spectroscopic data, and also other advantages, limitations and the wide range of applications for this characterization technique will also be covered in this lecture. You will also understand after going through this lecture what is Born-Oppenheimer approximation, the Beer-Lambert law, what is molar absorption coefficient, and finally, how do you plot and analyze an absorption spectra. Till now, we have discussed one characterization technique, that is X-ray diffraction, and we spent nearly 2 lectures on that technique. That technique was used for ensuring and collecting data so that you can extract information regarding phase formation, the type of crystal lattice and various other parameters related to a unit cell formation. Now, we have extensively used the concept of semiconductors in our earlier modules, and we have defined metals, semiconductors and insulators in terms of the difference in their band gaps. The first question which we need to ask is, how do we actually calculate the energy band gap in such materials? And one of the most common technique which is used to determine this band gap is the UV visible spectroscopy technique. So, this technique becomes extremely useful for our course, and if you go to laboratory, you will find that this is actually a very simple technique, but again it can give you lot of information. Spectroscopy is primarily the measurement and interpretation of the interaction between the incident electromagnetic waves. The moment I mention electromagnetic waves, please remember 2 things should cross your mind, that it has an E component and it has a B component. So, in spectroscopy, you are actually analyzing the interaction between the electromagnetic waves and matter characterized by changes which can be at the nuclear level, the molecular level or at the electronic states. So, this is what we are going to understand now. As we said, you have E component and B component in the EM wave. So, we have 2 types of techniques, one NMR, other UV-Vis. Just a very layman type difference. In NMR, you are talking about the interaction with the magnetic field of the electromagnetic waves with the magnetic dipoles which are present in a material, and in UV-Vis you talk about the interaction of electric dipoles with the electric field of the electromagnetic waves which are incident on the material where you are seeing these dipoles. So, NMR interaction is magnetic component, UV-Vis interaction with the electric component. NMR works in the radio frequency region. The nucleus and the electrons are considered to be tiny charged particles, and their spins is associated with a magnetic dipole. Now, this dipole interacts with the magnetic field of the electromagnetic waves, and if you go from one material to the other, the magnetic dipole in these materials change, and therefore, the signal which you obtain in NMR spectroscopy for different materials would be different. Similarly, in UV visible spectroscopy, what happens? During the excitation of valence electrons means you are exciting the valence electron, let us say from valence band to conduction band. Once there is a movement of electron, what is associated? There is a movement of electronic charge in the molecules, which subsequently changes the electric dipole moment. So, absorption, excitation, movement, change in the electric dipole moment, and a UV-Vis spectrum is generated when there is an interaction of these electric dipoles with the electric field component of the electromagnetic waves. So, this is the way you should understand the two types of techniques which are there to analyze the spectroscopic data. Generally, spectroscopy is classified in two categories. One, atomic spectroscopy or molecular spectroscopy. The earlier was the technique, and now we are understanding somewhat more in detail whether you are analyzing at the atomic scale or the molecular scale. In atomic spectroscopy, the changes in the energy takes place at the atomic level, as the name suggests, atomic spectroscopy, and you have a technique which is called as atomic absorption spectroscopy and many other. As the name suggests, molecular spectroscopy would be what? Very simple. In molecular spectroscopy, the changes in the energy takes place at the molecular level, and you have techniques like UV visible spectroscopy, IR spectroscopy, and few others. We will start with this, and in the next lecture we will start with our discussion on IR spectroscopy. Electronic spectroscopy basically arises due to the interaction of molecules with UV and visible range electromagnetic light. Now, the absorption of photon results in transition of a molecule or electron between two electronic states. So, you absorb energy, once you absorb energy, your energy is increased, and therefore, there is a transition. Such electronic transitions are accompanied by simultaneous transition between vibrational and rotational energy levels, and according to the Born-Oppenheimer approximation, the total energy of a molecule in ground state is given as E electronic plus E vibrational plus E rotational. This is the total energy of a molecule in ground state. And electronic spectroscopy can therefore be written in terms of the change in the energy when there is an electronic transition, and this change delta T is equal to change in electronic level, vibrational level, or energy of the rotational level. The frequency of the electronic transition is given by the Bohr frequency condition, that is nu. Nu is equal to delta Et by H, and this lies in the UV-Vis region. In UV visible spectroscopy, there is measurement of absorbance of the UV visible spectra, and the whole process is governed by the Beer-Lambert law. This law states that the amount of light that is absorbed by a solution is proportional to the concentration of the absorbing substance and the path length of the absorbing material. I have encircled few terms which are critical. What is the Beer-Lambert law actually indicating towards? That light will be absorbed. This is one. Solution. So, you are talking about the measurement probably when the sample is dispersed or you have formed a solution, is proportional to the concentration. So, if you have high concentration of material in the solution, then the response may be different from the condition when the concentration is much lower. So, the concentration of the absorbing substance, this after the term concentration of what? Of the absorbing substance, the substance which will absorb the energy from the incident UV light. So, you have a substance which will absorb energy. So, concentration is the one thing which will decide what is the output, and the second is the path length or thickness of the absorbing material. So, what is the nature of the material, how thick that material is, will also define what would be the output you will obtain. And mathematically the expression is the absorbance A is given as log of I0 by IT, where I0 and IT are the intensity of the incident light and transmitted light respectively, and that can be written as epsilon CL, where epsilon is the molar absorptivity coefficient in liter per mole per centimeter, C is the concentration, and L is the path length of the sample in centimeters. So, this is what is mathematical expression of the Beer-Lambert law. What is the importance? The basic importance is that the absorbance is proportional to concentration and we have a linear relationship if epsilon and L are considered as constant. Using this relationship, a quantitative analysis of sample, that is concentration of an unknown sample, can be determined. So, what will you do? You will have a sample or a solution with 0 concentration of the absorbing material. You will get an output corresponding to an incident electro or UV visible electromagnetic ray. Then you add C1 concentration, the output will change, and then you can draw the absorbance as a function of increasing or changing concentration, and you will get a curve. And if that is the standard curve which you have obtained, after some time if you perform the same measurement for an unknown sample where the initial solution or the fluid in which the material that is absorbing is dispersed is the same, then you can extract the information about the concentration of the absorbing material in a unknown sample. Very simple way of performing the experiment. The law clearly is able to give us a protocol by which we can perform the experiment to determine the concentration of a particular absorbing substance in an unknown solution. But there is a limitation. The main limitation is that the absorption behavior can only be successfully explained in dilute solutions up to, let us say, concentrations of 0.01 molar. And if the concentration increases, the absorption coefficient and refractive index of the sample changes with the increase in concentration, and then the analysis becomes a bit more complicated. The law is not applicable in the case of suspensions, as scattering of light due to impurities may occur and the whole process is much more complex. In addition, fluorescence or phosphorescence processes may occur as they take place in the same wavelength range of UV visible, and then the analysis of data becomes more difficult. Strict adherence of an absorbing system to this law is only observed when radiation used is monochromatic. So, if you use any light which has, let us say, components which are not monochromatic. So, if you have a source which is sending out more than one wavelength, then you must use filters to only send one wavelength. If you use radiation which is not monochromatic, then using this law it is difficult to obtain the concentration in solutions for the material which is absorbing the UV visible light. This is typically what you do. You prepare 4 or 5 standards of unknown concentration analyte, and then you have the data which is plotted as a function of absorbance and concentration. After you have prepared the calibration curve, you can then obtain epsilon from the slope of the calibration curve for a given wavelength. And concentration of an analyte in the sample can be obtained from the calibration curve using the Beer-Lambert's law. If you now have another solution where the same material is dispersed or substance is dispersed, but the concentration of that substance is not known in the solution. So, that is the way you perform this analysis. Please note that this measurement will give you reliable data only when you are using very dilute solutions or you are performing the measurements when system is in the vapor phase. The sample is dissolved in some suitable solvent. What do you mean by suitable solvent? That is the one which does not itself absorb radiation in the region under investigation. Otherwise, they will also start giving you signal. And obviously, the chosen solvent should be inert to the sample. So, there should not be the case that you start having reaction between the solvent and the solute. So, once you have set these conditions, you will find that this lead to a condition of preferred conditions where non-polar solvents are mostly recommended for such kind of measurements. Now, let us start moving towards instrumentation of the whole UV-Vis spectrophotometer, and then we will discuss about the data collection and then how that is used to extract information regarding the energy band gap in semiconductors. So, you have a light source, you can have different types of light source. Then you have monochromator as discussed earlier, so as to ensure that one wavelength is incident on the sample. So, in the instrument you have two sample holders, one where you will put the reference cuvette and in the other where you will have the sample cuvette. The reference cuvette has the pure solvent in it. It is important to set the reference cell to 0, so that the data which you get from the other sample holder is actually coming in only from the absorbing material, because the signal which can originate from the cuvette or the solvent is collected from the reference cuvette and that is removed from the signal which is obtained from the sample cuvette. So, there are two types of sample places to put your samples. If you are using visible light, cuvettes are made up of PMMA, polymethyl methacrylate, polystyrene or normal glass. For UV light, the cuvettes are made up of quartz glass or special type of plastics are used. Then once I have the source, the sample, the light interacts with the sample, then you have a signal output. Once you have a signal output, you must collect this signal and then analyze the signal. That means you must have a detector, and the detector is a typical photo multiplier tube which you have studied in many courses. What do they include? There is a photoemissive cathode that absorbs, and then you have the emission of electrons, and then you have the other components of the photo multiplier tube which you have been studying in earlier classes. This is what the UV visible spectrophotometer typically looks like. Sorry, I will repeat, no, pen not active. This is the instrumentation of the UV visible spectrophotometer. So, this is a typical instrument and this is the picture of the chamber where you have the sample holders. And you will see the video in the next slide and things will become very clear. So, what happened? You have the light source, the mirror which will reflect the light, then you will direct these light using diffraction grating. These will fall on the half mirror, half of the intensity will go towards, let us say, mirror 4 and the remaining will go towards mirror 3, that is 50% of the intensity will be falling on mirror 3 and 50% will be falling on mirror 4. The light from mirror 4, let us say, will cross the reference cuvette, and the light which is reflected from mirror 3 will pass through the sample cuvette, and then what you obtain would be the reference beam and the sample beam. Sample beam detected by detector 1, reference beam detected by detector 2. This is what it is, the typical instrumentation. So, you see the optics play a very critical role, and therefore, while you are using these instruments, you should be very careful that you should not disturb these instruments, otherwise the optics, which are very sensitive to vibrations, will change and the data will not be the one which is expected, or you will get data that needs to be again calibrated with some standards. So, let us see the way this is happening. You have the source, then the optics, then the sample holder. This is a typical solution which is prepared, and either you can use a standard or you can use the one which is having the reference in it. After you have installed the sample in the sample holder, you close the lid and you run the program. Once you have closed the lid, then you will set the program condition or experimental conditions. You will define the range in which you want to have the absorbance, and then you will run the scan. But before you run the scan, what you need to do, please ensure that the instrument is kept switched on for at least 15 minutes for warming up, because the deuterium lamps and the tungsten halogen lamps, they need to warm up before they can be used. And typically it is always advised that you keep the instrument in a switch on mode for 15 minutes before initiating the whole experiment. So, then you set up the software, you will define all the conditions, and then you will tell the, let us say, the number of cells, what is the number of the solution which you will be using, the kind of solution you are using, and the various other parameters which you are knowing about the sample. You will give the sample name, the wavelength, all the details about the sample you will be defining. For example, in this we are showing the scan setup. We have defined the range from 2. So, what is the wavelength where we are scanning, and what is the scan step, at which steps you would like to carry out the measurement. This is just the display range, the y axis, just so that if you are analyzing online, you get an idea of how to you see the spectrum as it is collected. Along with that, you can define the backgrounds, the colors, or everything. Typically you play with the graphs. Once you have done it, you play the play button, and then the data collection starts, and you will see that you are obtaining the absorbance as a function of changing wavelength, and you are getting the data. At the point where the sample is having the excitation, you will see some peaks. Otherwise, you will see the typical background. Once it has been collected, you can save the data and then you can refine it. Once you have obtained the absorbance data, you can use the torque relation to calculate the band gap. So, for example, you have two types of semiconductors, the direct band gap semiconductor and the indirect type. The torque relation is based on the assumption that the energy dependent absorption coefficient alpha can be expressed as alpha h nu raised to the power of 1 by n is equal to B into h nu minus E g, where E g is the band gap, h is the Planck's constant, nu is the photon frequency, and you have the absorption coefficient as alpha. The factor n is half for direct band gap and equals to 2 for indirect band gap. So, if you are measuring a material where you are seeing direct band gap, then you will plot alpha h nu as a function of h nu. So, you will plot alpha h nu square as a function of h nu, and you will get a curve, and in the region where you can fit a linear line, you will fit a linear line and then extrapolate it. The intercept on the x axis will give you the band gap, and in case of indirect type material, you will plot alpha h nu raised to the power of half as a function of energy, that is h nu, and you will get a similar curve and then you will fit a linear line. This is what you actually perform. This is the data you have obtained for, let us say, graphitic carbon nitride. Then you plot alpha h nu whole square as a function of h nu energy, you get a plot, and then this is the linear region which is shown in the red solid line. You plot the red solid line and extrapolate, and the point it intercepts with the x axis is the value for band gap, and this is, for example, 2.10 electron volts for graphitic carbon nitride. And this is the way the band gap in semiconductors are estimated. Other applications of UV-Vis range from the field of nanotechnology to high performance liquid chromatography that can be used in polymers, rubbers, biophysics, nanofluids. A large number of applications are there. You can also talk about understanding the electronic transitions in organic compounds, or there are other applications which are very common and used extensively, like understanding the kinetics of chemical reactions. So, what you do? You pass the UV radiation through the sample, and as the chemical reaction takes place, there is a change in the absorbance, and from there you can extract information about the kinetics. You can use this technique to talk about the concentration of nucleic acid, such as DNA or RNA in any biological samples. So, let us end this lecture by clearly indicating that UV visible spectroscopy is one of the most fundamental spectroscopic technique for qualitative and quantitative analysis of samples which have been discussed during this course, and this technique actually makes the determination of band gap in semiconductors a very easy concept and is also routinely used. These are the references which were followed while preparing this lecture or for obtaining the data. And in the next lecture, we will talk about another technique which is the FTIR technique for sample characterization. And I thank you for attending today's lecture.